All right. Okay, so today we are going to talk Bootstrap, and kind of the what we've been talking about is doing statistical inference, and one of the key ideas in statistical inference is this concept of a sampling distribution. Right? So in statistical inference, we want to take our sample and make conclusions about the population. And in order to do that, we have to know what the sampling distribution looks like. And the sampling distribution is the distribution of kind of all possible sample statistics that can be generated from a given population. And in your intro stats class, the sampling distribution is assumed of the mean is assumed to be normal based on the central limit theorem. Okay, so you use the central limit theorem and you say, based on the central limit theorem, when we take a bunch of random samples from some population and we look at the means of those different random samples, those means will follow a normal distribution. Okay, it'll be centered at mu, the population mean. It'll have a standard deviation or standard error of sigma divided by the square root of n. So that's going to be your sampling distribution. That's based on the central limit theorem. On Monday, we talked about the randomization test. And the way, what we did was we said, let's assume the null hypothesis is true. Let's create a sampling distribution under the null hypothesis. And when we create a sampling distribution under the null hypothesis, we said we're going to assume that the assignment of treatments was done randomly, which means any other permutation of those treatment assignments are equally valid, and we can create a sampling distribution of numbers and things like that by just re-randomizing those treatment assignments. Okay, and so we said we can just shuffle these things, and we explored that on Monday. Okay, today we're going to learn Bootstrap, which is just another way to create another sampling distribution. It's just the assumptions we make in Bootstrap are going to be different from the assumptions we make in randomization tests, right? And so in statistics, it's unavoidable to, you have to make assumptions. That's the whole idea in statistics, is that we are making assumptions about the population or the sampling distribution. In your intro class, you're assuming that sampling distribution is normal because of the central limit theorem. In randomization tests, you're assuming that exchangeability is valid, that because the treatments were assigned randomly, any other arrangement of treatments is equally valid. Okay? And in Bootstrap, we're going to be making different assumptions. Okay? And we have to make assumptions because the whole idea of statistics is I'm only going to observe a small thing. And because I'm going to make some assumptions about the relationship between my small sample and the big population, which is too big for me to observe directly, because I'm able to make some assumptions about that, I can then make conclusions about the population which I haven't observed directly. Okay, and so that's kind of the whole point. So we do have to make assumptions, and it's just depending on the situation, the kinds of assumptions you might want to make are going to vary. And so randomization tests, we're assuming the assignment of treatments is random, and thus any other arrangement, any other permutation of assignments is equally valid. Bootstrap, we're going to make a different set of assumptions, and we're going to talk about those today. But again, key idea here is we're generating a sampling distribution. And the reason why we want a sampling distribution is so that we can take a look at our observed sample, compare it to the sampling distribution created under the null hypothesis, and say, is my sample that I have, is this likely to form looking at the sampling distribution, or is it very unlikely to form under the sampling distribution? Okay. So I'm hoping that that's okay. And so we're talking sampling distributions, and Bootstrap is just another way to make a sampling distribution. Okay. So this term Bootstrap comes from the phrase to pull yourself up by your bootstraps, which if you're not familiar with the idiom, It's the idea of helping yourself out without external help, okay? So I tried to look up where this phrase came from because somebody told me that it comes from this German folktale thing, and I looked it up. Indeed, I did find some articles on the internet, which is not necessarily the most reliable place of information, that confirmed this tale, but there were also other stories of where this thing originated, so I'm not sure, okay? But you know, in the German folktale, the guy, our folk hero, got stuck in a swamp, okay? He got stuck and he couldn't get out, and so the way he got himself unstuck was he pulled himself out by his bootstraps, right? So he just grabbed his bootstraps and yoink, he got out of the swamp. It's a silly idea, but the idea is he fixed his problem without external help, okay? And so when we are talking about Bootstrap in statistics, we are talking about a method to generate a sampling distribution without the need to collect additional data, without the need to access our population directly. We're going to just take the one sample that we have, and based on this one sample, we're going to generate a sampling distribution, okay? We're going to make a few assumptions, but we're going to be able to generate a sampling distribution. And there's parametric and non-parametric Bootstrap, and I'll talk about both of these now. And in the last class, we only had time to get into the parametric Bootstrap in detail, and then I guess I'll have to talk about the non-parametric Bootstrap on Friday, but it'll be quick. So, okay, so this is how it's going to work. With parametric Bootstrap, we are going to make certain assumptions about the population, and specifically, we will assume that the population follows a specific parametric distribution, okay? And what I mean by a parametric distribution is these are all those kind of distributions that you learned about in your 100A, 100B class, okay? Where, you know, you have like the normal distribution, but you also have like the Poisson distribution and exponential distribution and I don't know, binomial and negative binomial and I don't know what other hypergeometric distributions and all of these things that you learned about. You're going to say, well, I paid attention in my 100B class, and so I know exactly when we should apply these distributions, and this is a situation where I can apply this distribution, and I'm going to do it, okay? And that's what we do in parametric Bootstrap. We say, I'm going to assume that the population follows this theoretic distribution. And, you know, when you have a theoretic distribution, those theoretic distributions are defined by some kind of parameter, right? Normal distribution is defined by the mean and the standard deviation, your mu and your sigma. Your exponential distribution is defined by your rate parameter, lambda. Your beta distribution has two shape parameters, alpha and beta, and things like that. And what we'll do is we're going to say, I'm going to select my parameters based on the sample I have, okay? I'm going to assume that my sample is coming from this thing, and based on the sample I have, I'm going to use this value as an estimate of the population parameters. And now that I have assumed what the population distribution looks like, I can now generate new samples from this distribution, and if I'm able to generate samples from some distribution, I can then create a sampling distribution. And now that I have a sampling distribution, I can do inference, okay? So one example is we might say the population is a normal distribution with the mean equal to our sample's mean and the standard deviation equal to our sample's standard deviation. Then we simulate random samples coming from that theoretic normal distribution with this mean and standard deviation. We do this to generate a sampling distribution, and with the sampling distribution we do statistical inference. Is that idea okay? And so depending on your situation, maybe you don't want a normal distribution, right? So we use a normal distribution when what? When our variable is continuous, unimodal, and symmetric, right? Those are kind of our key things. We would use, so if we have, you might have a different scenario where it's not appropriate to use a normal distribution. Maybe you're, I don't know, what would be the classic example of using the Poisson distribution? What's a classic situation where you use the Poisson?
Rate of arrivals.
What's that?
Rate of arrivals.
The rate of arrivals are basically the number of people standing in line, I guess the number of arrivals within a certain amount of time, the number of events within a certain amount of time. So you have like, I don't know, the Prussian army horse kick death data. You guys know about that? Okay, no, never mind. All right, look it up. It was a classic example of the use of the Poisson distribution from the Prussian cavalry. Or you might say how many customers arrived within this window of time at the bank and things like that. That would follow a Poisson distribution. Okay, if you're looking at wait times, like if you're standing in line and how long do you have to wait until you get to see the teller, that's gonna, or time between arrivals would be exponential and things like that. So depending on your understanding of these probability distributions, you would say, oh, this is a situation where I should use this probability distribution, and if I'm going to use this probability distribution, I'm going to estimate that my parameter is this based on my sample, and then we can generate new random samples that way. So that's parametric bootstrap. So you say, here's my sample. My sample has these statistical estimates, this sample mean, this sample standard deviation, or this sample rate. And based on that, I'm going to assume the population follows this theoretic distribution with these properties. In non-parametric bootstrap, we do not make distributional assumptions about the population. We don't say the population follows the normal, or we don't say the population follows Poisson, or one of these theoretic distributions that you learned about. Instead, our big assumption relies on the fact that our sample was randomly obtained from the population. And we say if my sample was randomly obtained from the population, then I can assume it should be representative of the population. Okay, and this is kind of the big assumption we're making. Here's my sample. I survey, I got a random sample of 1,000 people from the United States, and I'm going to assume this random sample is representative of the entire population. And so to create a sampling distribution, I have to be able to sample from the population. Parametric bootstrap, we said, I'm assuming population has this shape, okay? Over here, I want to sample directly from the population. I don't have the population. I have a sample that I'm assuming is representative. And so to create my population, what I do is I take my sample and I just make like 1,000,000 duplicates of it. I just duplicate my sample. I clone my sample like 1,000 times or 1,000,000 times or whatever it is. And now I have this big thing that should look kind of like the population. Okay, so you can see the problem. If your sample is not representative of the population, you're going to just magnify that issue. Okay, but we're hoping that because it was a random sample, it should be representative of the population, and so we just take our sample, we clone it, I don't know, like 1 billion times, and now I have a population, like a quote unquote pseudo population here, and I can draw samples from that to generate my sampling distribution. Is that okay? Because the sampling distribution is the idea that we're going to draw from our population random samples a whole bunch of times to see what kind of values I can get from my sampling distribution. So the way we create our population this time is not assume some mathematical shape, but we're going to say my sample is representative of the population, so I'm going to clone it duplicate it a million times. I have my population now, and now I can draw from that population. Okay. So it turns out that you don't actually even have to go through the process of duplicating your sample a million times. Okay. If you just sample from your sample with replacement, that's equivalent to making an infinite number of copies of your sample. Okay, so if you sample, so it's a little weird, but if you pick from your sample with replacement, it's effectively the same as making infinitely many copies of your sample. Is that okay? So you don't actually have to physically duplicate it like a million times. You can just sample from your sample with replacement. And so that's what we do in non-parametric Bootstrap. We will resample our sample with replacement, and that's effectively turning your sample into a population by duplicating it infinitely many times. And when we do that, then we can create a sampling distribution, and then we can do statistical inference there. All right. Okay. So this might sound kind of like randomization tests, but not. They're a little bit different. Okay. So so here's kind of our the differences, right? So if the data we have came from random sampling, we can use non-parametric Bootstrap, because if our data came from random sampling, it's probably an okay assumption to assume that your random sample should be representative of the population because it was obtained randomly. Okay. If your data was obtained via random sampling and you're willing to make mathematical or distributional assumptions about the population, you can do parametric Bootstrap. Okay? You're going to say, my data was obtained via random sampling, therefore it should be representative of the population. I'm going to make these distributional assumptions, but to specify my distribution, I need a parameter, and because my random sample should be representative of the population, it should be safe to use my sample's mean or my sample's rate or my sample's whatever statistic as the parameter of the population. That's parametric Bootstrap. Randomization tests, however, generally apply when you have a random experiment. In a random experiment, your sample was not obtained randomly. Okay? When you do a controlled experiment, the data you have, your participants, are not going to be a random sample of the population. Okay? So you cannot assume that your participants are representative of the population. However, the assignment of treatments was done randomly. Okay? And because the assignment of treatments was done randomly, any other permutation of those treatments could have happened, should have been equally valid under the null hypothesis, and therefore we can do permutations of those random treatments, of those treatment assignments. And that's what we do in a randomization test. We assume our treatment assignments are exchangeable or have exchangeability with any other set of treatment assignments. Are those distinctions okay between kind of our scenarios? Okay, sorry for this wall of text. This comes from the textbook Comparing Groups, okay? And so new textbook, again, available for free. As long as you're connected to the UCLA VPN, you're gonna, you can download it. And this is from chapter 7, the Bootstrap tests, okay? And we are going to look at this data set for our kind of our Bootstrap, okay? And so, so this data set comes from a study done in 2006, and the researchers, were interested in immigration to the United States, particularly from Latin American countries, and what they wanted to do was they wanted to see, they were interested in the education achievement levels of immigrants from Latin American countries. Okay, so they wanted to know, you know, who graduates from high school and who goes to college and who gets this degree and that degree and whatever. Okay, and so and they're in the United States. We get a lot of immigrants from all the Latin American countries, but probably the largest group comes from Mexico. And so the researchers were interested, is there a difference between the education achievement levels of immigrants from Mexico versus immigrants from other Latin American countries? This is what they did. They took data from the 2000 census, okay, because this was done in 2006, so their most recent census data came from the year 2000, and they looked at this, okay? And so when we look at our data set, these are kind of the variables that they're looking at. And so here that we're looking at, there's actually only 150 observations in our data set. And this data comes from kind of like the long form census. So there's going to be a census done next year, and most people get the short form, which just says what's your name and what's your birthday. Okay, and there's a lot of debate about what other questions they can put on the short form, and there's a big heated controversy about whether they should put a citizenship on the question on the short form, because if you're skeptical of the government, you know, including this kind of question may make you less likely to fill out the census, and if you don't fill out the census and your state gets undercounted, then you might have fewer representatives in the government and things like that. So there's all sorts of consequences to the census. It's very important to get an accurate count, and so but anyway, there's the short form, and then there's a long form, and the long form goes out to a random sample of people in the United States, and they ask all sorts of questions. They ask, you know, what's your race and your ethnicity, and what's your occupation, and blah, 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 and your education achievement level, and this and that. Okay, so they ask all of these questions, and here we look at 150 Latino immigrants from Los Angeles, okay? And really, we are just interested in the relationship between two variables. One of them is achievement, okay, which is educational achievement level. And unfortunately, we don't actually have any idea what these numbers mean. All we know is that 1 is low, 100 is high, but as far as the book goes, it doesn't tell us, like, what does the number 50 represent? Does 50 mean they graduated from high school, or does 50 mean they only achieved, you know, 11th grade or 10th grade or whatever? It doesn't say, okay? We don't know what graduating from college turns into as far as, you know, level 1 through 100 or things like that. So, but all we know is just 100 is small, 1 is small, and 100 is big, okay? And it's somehow coded from our data. And then the other variable that we're interested in is, did the individual come from Mexico, yes or no, okay? So no, 0, no would be they came from a different Latin American country, okay? All right, and then, you know, there's other questions, you know, the age at the time of immigration, when did they immigrate, when did they arrive in the United States, things like that. Are they fluent in English? But we are not interested in those variables. And so here's just kind of the first 6 rows in our data. We're looking at our achievements, you know, 59.2, 63.7, 62.4. I have no idea what the difference is between what these two things are, but whatever, they've gone and they said, your education achievement level is 63.7 and yours is 62.4. And so somehow they coded the education achievement in some kind of number here, okay? And then, and here we have 1s for people who came from Mexico, 0 for people who came from a different Latin American country. And here we can just do some summary statistics, and we can say, what is the mean and standard deviation, and how many do we have? And so for the variable Mexico, 0, meaning they came from a they came from a different country, not Mexico, so, Honduras, Guatemala, something, we have 34 in our data set of 150, okay? And then the mean was 64.5, and the standard deviation is 13. And then for the immigrants from Mexico, we have 116. Mean is 58.6, standard deviation 15.6. Okay, and the question is this difference between 64.5 and 58.6, is that significantly different from 0? Okay, is this difference from here to here, is there actually a difference, or is it not statistically significant? Okay, so why is this showing up here? I don't know. Okay. Here's a box plot showing down on the bottom we have countries other than Mexico, and up on top we have immigrants from Mexico. This is kind of what our thing looks like. If we create a density plot, sorry, brain just went blank for a second. If we create a density plot, the blue is for Mexico, and the orange or pink or red or whatever the color this is, that's for other countries, okay? And if we did a traditional analysis, it would look something like this, okay? Our null hypothesis, we would do a t-test, right? Our null hypothesis is that the mean education achievement level of Mexican immigrants minus the mean education achievement level of other Latin American country immigrants, that difference is equal to 0, okay? And then the alternative is that difference is not 0. And if we do this with a 2-sample t-test, okay, we get a p-value of 0.04597. What kind of assumptions are we making when we do a t-test? Assumptions for a t-test. Okay, what about what assumptions are we making about the shape of this sampling distribution? That it's normal or Gaussian, okay. What about, and so for the null hypothesis, we're assuming that both populations have the same mean, and what else? Probably that their variances are also equal, okay? If you don't set the variances equal, if you are not going to assume that they're equal, then it's technically called a Welch 2-sample t-test or a Welch test. But anyway, we get a p-value of around 0.0459, okay, 0.046. All right, so we will talk parametric bootstrap, okay? So in parametric bootstrap, we're going to make assumptions about the shape, and we're going to say the population has this mathematical theoretic distribution, okay? And so again, our null hypothesis is mu Mexico minus mu other countries equals 0, okay? And we want the sampling distribution of the difference between sample means, okay? And so the null hypothesis says that the education achievement levels are equal for both groups. And if this is the case, and if we assume that the variances are equal for both groups, then the null hypothesis effectively states that the data for both groups come from the same population. That my values of, that my sample of education achievement levels for Mexican immigrants come from this population, some unknown population, and the values for the education achievement levels of other countries come from the same population, because they're both going to be normal. They both, like, if you have two normal populations with the same mean and same variance, they are the same population, right? That's what we are going to say under parametric bootstrap, okay? And so if we look at our data set, we have 116 coming from Mexico, 34 coming from other countries. And we, again, look at our summary statistics. The mean is 64.5 and 58.6. And so the difference between the two means that we observed is 5.9, okay, 5.9. And so when we ask, what is our p-value, we're going to ask, how often will this happen? What's the probability of this thing happening if I draw two random samples, one size 116, another one size 34, if they're both coming from the same population, how often am I going to get a difference of 5.9 or more? Okay, well, I guess a magnitude, absolute value of 5.9 or more. That's what we want to know. Okay, so how often do I get this observed difference just from random chance if I'm drawing one sample from this population and another sample from the same population? So we want to create a sampling distribution. So when we do this sampling distribution, in parametric Bootstrap, we're going to make several major assumptions, okay? And we can have debates about whether or not these are good assumptions, okay? If you're willing to make these assumptions, then this is okay. If you say these are bad assumptions, then don't do parametric Bootstrap, okay? But so one major assumption is that the population is normally distributed. Like if we looked at the education achievement levels of everybody, that's going to be normally distributed. And we can go back to this slide and we can say, well, could this, I don't know where the statics come from, but could this come from a normal distribution? We look at this and we go, I don't know. And some people might say, yeah, that's okay. And other people might say, no, that's not okay. But that's what we're going to assume. For parametric Bootstrap, we're going to assume that it comes from some specified distribution, and in our case, that it's going to be a normal distribution. The other big assumption is that this population from which we are drawing our samples, that the mean of this population is going to be the overall mean of our data set, and the mean standard deviation of this population is going to be the overall standard deviation of our data set. Okay, so we're going to look at the mean of all 150 people. So we're going to put all of the immigrant education achievement levels into the same pool, and we're going to look at that overall mean and that overall standard deviation. We're going to use those as what defines our theoretic distribution. Okay, and this is based on the assumption that our sample was randomly obtained from the population, and therefore the summary values, the summary statistics are representative, are okay for the population. Okay, so this is what we do. I get the overall mean, take the entire achievement column, throw that into the mean function, and I get M. Take the entire achievement column, take the standard deviation, and throw that into S. So I have the overall mean, overall standard deviation, and then I'm going to create my sampling distribution. And the way we do this is, just for reproducibility, I'll set a seed here. I'm going to create an empty vector of 10,000 values. And what I do, again, because under the null hypothesis, we're assuming my samples come from the same population, I'm going to use our norm. We're going to assume that our samples come from a normal distribution. I'm going to draw 116 values from a normal distribution with mean M and standard deviation S. And that's going to be our kind of our stand-in for the values for the immigrants from Mexico. And then we do the same thing, okay, except I draw only 34 because that's how many we have. And this will come from the same population, our norm with mean M and standard deviation S, but we're going to draw a sample of 34, and that will go in as our stand-in for the values for other countries. We calculate the mean for Mexico, and we subtract off the mean for the other countries, and we store that difference into our vector of diffs. Okay, and we do this 10,000 times. So this is going to produce a sampling distribution of 10,000 different differences that we've observed just from random sampling. Okay, and so so to get our p-value, we say how often, just from random sampling, did we get a difference that was greater than or equal to our observed difference of 5.9 whatever, okay? So our observed difference was 5.9, and we said how often do we get something by random chance greater than or equal to our sample's summary statistic. And this says after 10,000 times, it happened 453 times, or about 4.5%, okay, with a probability of about 4.5%. So that lines up almost exactly with what our t-test says, right? So our t-test says we're going to get about 4.6%, And by random sampling, when we created our sampling distribution, we got a difference of around 0.045. That this happened around 0.0453 of the time. So just right about the same, okay? Which makes sense, because if we think about the distributional assumptions of the t-distribution saying that the sampling distribution is normal, if we're going to make assumptions that the population is normal, then we're basically making the same assumptions when we created this sampling distribution ourselves, right? So we're making something like that, and so because we know that if you have, this should have been covered in, I don't know, 100B. You guys are taking 100B right now or something. That if you have two normally distributed random variables, that the difference between those two random variables will also be normally distributed with a mean of mu A minus mu B and a variance of variance A plus variance B, right? So we're basically we're saying that, and so we get this. So the fact that this matches up with our t-test, which makes similar distributional assumptions, is not surprising, okay? But and so anyway, you get a p-value of something just under 5%, and so depending on your significance level alpha, you might say this difference is significant or this difference is not significant. So if your alpha is 5%, you will say, okay, we're under 5%, therefore my difference is significant. Publish my paper, right? But if you use an alpha that's a little bit more conservative, you say we're going to use alpha of 1%. I really need to have data that really supports this idea before I'm going to make some kind of conclusion. Then we would say it's not significant, right? Because this is bigger than 1%. So that's what we have there. We can kind of take a look at this, and this is the distribution of achievement levels that we observed. And remember, our big assumption that we made back here, okay, was that our population is normal. And so if you look at this and we say, well, could this have come from a normal population? Maybe, maybe not, okay? And it's hard to say, right? So if it was a bad assumption to assume that the population was normal, then doing this parametric bootstrap is not a good idea. If you feel comfortable with that assumption, then you can go ahead and do this. Okay, are there any questions on this parametric bootstrap stuff? I feel okay. Okay, I'm going to we'll